of the character of the train at a definite instant. Furthermore, there are different types of such convergence to simplicity. For example, we can converge as above to the limiting character expressing nature at an instant within the whole volume of the train at that instant, or to nature at an instant within some portion of that volume, for example within the boiler of the engine, or to nature at an instant on some area of surface, or to nature at an instant on some line within the train, or to nature at an instant at some point of the train. In the last case the simple limiting characters arrived at will be expressed as densities, specific gravities, and types of material. Furthermore, we need not necessarily converge to an abstraction which involves nature at an instant. We may converge to the physical ingredients of a certain point track throughout the whole minute. Accordingly, there are different types of extrinsic character of convergence, which lead to the approximation to different types of intrinsic characters as limits. We now pass to the investigation of possible connections between abstractive sets. One set may cover another. I define covering as follows. An abstractive set P covers an abstractive set Q when every member of P contains as its parts some members of Q. It is evident that if any event E contains as a part any member of the set Q, then owing to the transitive property of extension, every succeeding member of the small end of Q is part of E. In such a case I will say that the abstractive set Q inheres in the event E. Thus when an abstractive set P covers an abstractive set Q, the abstractive set Q inheres in every member of P. Two abstractive sets may each cover the other. When this is the case, I shall call the two sets equal in abstractive force. When there is no danger of misunderstanding, I shall shorten this phrase by simply saying that the two abstractive sets are equal. The possibility of this equality of abstractive sets arises from the fact that both sets, P and Q, are infinite series towards their small ends. Thus the equality means that given any event x belonging to P, we can always by proceeding far enough towards the small end of Q find an event y which is part of x, and that by proceeding far enough towards the small end of P we can find an event z which is part of y, and so on indefinitely. The importance of the equality of abstractive sets arises from the assumption that the intrinsic characters of the two sets are identical. If this were not the case, exact observation would be at an end. It is evident that any two abstractive sets which are equal to a third abstractive set are equal to each other. An abstractive element is the whole group of abstractive sets which are equal to any one of themselves. Thus all abstractive sets belonging to the same element are equal and converge to the same intrinsic character. Thus an abstractive element is the group of roots of approximation to a definite intrinsic character of ideal simplicity to be found as a limit among natural facts. If an abstractive set P covers an abstractive set Q, then any abstractive set belonging to the abstractive element of which P is a member will cover any abstractive set belonging to the element of which Q is a member. Accordingly, it is useful to stretch the meaning of the term covering and to speak of one abstract element covering another abstractive element. If we attempt in like manner to stretch the term equal in the sense of equal in abstractive force, it is obvious that an abstractive element can only be equal to itself. Thus an abstractive element has a unique abstractive force and is the construct from events which represents one definite intrinsic character which is arrived at as a limit by the use of the principle of convergence to simplicity by diminution of extent. When an abstractive element A covers an abstractive element B, the intrinsic character of A in a sense includes the intrinsic character of B. It results that statements about the intrinsic character of B are in a sense statements about the intrinsic character of A, but the intrinsic character of A is more complex than that of B. The abstractive elements form the fundamental elements of space and time, and we now turn to the consideration of the properties involved in the formation of special classes of such elements. In my last lecture I have already investigated one class of abstractive elements, namely moments. Each moment is a group of abstractive sets, and the events which are members of these sets are all members of one family of durations. The moments of one family form a temporal series, and allowing the existence of different families or moments, there will be alternative temporal series in nature. Thus the method of extensive abstraction explains the origin of temporal series in terms of the immediate facts of experience, and at the same time allows for the existence of the alternative temporal series which are demanded by the modern theory of electromagnetic relativity. We now turn to space. The first thing to do is to get hold of the class of abstractive elements which are in some sense the points of space. Such an abstractive element must in some sense exhibit a convergence to an absolute minimum of intrinsic character. Euclid has expressed for all time the general idea of a point as being without parts and without magnitude. It is this character of being an absolute minimum which we want to get at and to express in terms of the extrinsic characters of the abstractive sets which make up a point. Furthermore, points which are thus arrived at represent the ideal of events without any extension, though there are in fact no such entities as these ideal events. These points will not be the points of an external timeless space, but of instantaneous spaces. We ultimately want to arrive at the timeless space of physical science, and also of common thought which is now tinged with the concepts of space. It will be convenient to reserve the term point for these spaces when we get to them. I will therefore use the name event particles for the ideal minimum limits to events. Thus an event particle is an abstractive element, and as such is a group of abstractive sets, and a point, namely a point of timeless space, will be a class of event particles. The required character of the abstractive sets which form event particles would be secured if we could define them as having the property of being covered by any abstractive set which they cover. For then any other abstractive set which an abstractive set of an event particle covered would be equal to it, and would therefore be a member of the same event particle. Accordingly, an event particle could cover no other abstractive element. This is the definition which I originally proposed at a congress in Paris in 1914. There is, however, a difficulty involved in this definition if adopted without some further addition, and I am now not satisfied with the way in which I attempted to get over that difficulty in the paper referred to. The difficulty is this. When event particles have once been defined, it is easy to define the aggregate of event particles forming the boundary of an event, and thence to define the point contact at their boundaries possible for a pair of events of which one is part of the other. We can then conceive all the intricacies of tangency. In particular, we can conceive an abstractive set of which all the members have point contact at the same event particle. It is then easy to prove that there will be no abstractive set with the property of being covered by every abstractive set which it covers. I state this difficulty at some length because its existence guides the development of our line of argument. we have got to annex some condition to the root property of being covered by any abstractive set which it covers.